Hello students, let us start with definition of onto linear transformation. Definition: a linear transformation, T from Rn to Rn is said to be onto if each b bar in Rn is the image of at least one x bar in Rn. Equivalently, T map Rn onto Rn when image of T is all of the domain here is codomain, all of the codomain R raised to Rn, that is T map Rn onto Rn, that is T map Rn onto Rn is for each b bar in Rn there exists at least one solution. There exists at least one solution for T of x bar is equals to b bar. Okay. The map T is not onto when there is some b bar in Rn for which the equation T of x bar is equals to b bar has no solution. Okay. See here, a linear transformation T from Rn to Rm is said to be onto if each b bar in Rm is the image of at least one x bar in Rn. Suppose this is your set Rn and this is suppose your set Rm. T is a linear transformation from Rn to Rm. When this linear transformation is onto, for each b bar in Rm has at least one image in at least one x bar in Rn, means each b bar in Rn is the image of at least one x bar in Rn. Okay, or equivalently, T maps Rn onto Rm when image of T is all of the codomain Rm. Okay, that is T maps Rn onto Rm if for each B bar in Rm there exists at least one solution for T of x bar is equals to B bar. The map T is not onto when there is some B bar in Rm for which the equation T of x bar is equals to B bar has no solution. Okay, a map T from Rn to Rm is onto when for each B bar in Rm there exists at least one solution for T of x bar is equals to B bar. Next, see one-to-one linear transformation. A linear transformation T from Rn to Rm is said to be one to one if each B bar in Rm is the image of at most one x bar in Rm. Okay, equivalently T is one to one if for each B bar in Rm the equation T of x bar is equal to B bar has either unique solution or none at all. The map T is not one to one when some B bar in Rm is the image of more than one vector in Rm. If there is no such a B bar, then T is 1 to 1. Students, see here a linear transformation T from Rn to Rm is said to be 1 to 1 if each B bar in Rm is the image of at most one x bar in Rm. Okay. That means for every vector in Rn has unique image in Rn, and you know that very well. This is a domain and this is a codomain. Okay. Equivalently, T is 1 to 1 if for each B bar in Rm, the equation T of x bar is equals to B bar has either unique solution or none at all. Okay. The map T is not 1 to 1 when some B bar in Rm is the image of more than one vector in Rm. Means suppose here y bar and its image is also b bar, then this is not a one-to-one linear transformation. If this y bar has image suppose b1 bar, then this map is 1 to 1 map. Okay, let us see one theorem. Let T from Rn to Rn be a linear transformation. Be a linear transformation. Then be a linear transformation. Then T is 1 to 1 if and only if and only if the equation, if and only if the equation T of x bar is equals to 0 bar has only trivial solution. Has only trivial solution. See proof of this theorem. Proof. Since T is linear, so T of 0 bar is equals to 0 bar. First of all, here we have to show that T is 1 to 1 if and only if the equation T of x bar is equals to 0 bar has only trivial solution. First we assume that T is 1 to 1. First we assume that T is 1 to 1. T is 1 to 1. Therefore, the equation T of x bar is equals to 0 bar has at most one solution by definition of one-to-one function, and hence only the trivial solution, and hence only the trivial solution. Okay. If T is not 1 to 1, if T is not 1 to 1, then there is B bar, that is the image of at least two different different vectors in Rn, say u bar and v bar. Here T is not one to one. T is a linear transformation from Rn to Rn. T is not one to one means there exists at least one v bar who is the image of two different vectors in Rn. Okay. That is T of u bar is equals to b bar and T of v bar is equals to also b bar. But T is linear. So T of u bar minus v bar is equals to, T is linear, so this can be written as T of u bar minus T of v bar. T of u bar, which is equals to b bar minus b bar, and this you will get 0 bar. But since u bar and v bar both are different, so their difference never be 0, is not equal to 0. Hence the equation T of x bar is equals to 0 bar has more than one solution. So either the two conditions in the theorem, are both true or they are both false. Are both true or they are both false. Means if T is 1 to 1, then T of x bar is equals to 0 bar has only trivial solution. If T is not 1 to 1, then T of x bar is equals to 0 bar has has more than one solution. Okay, this is the proof of theorem. Okay. Now we will see next theorem. Let T from Rn to Rn be a linear transformation. And let A be standard matrix for T. In previous video we have already seen what is a standard matrix for T. Then first one is T maps Rn onto Rn if and only if columns of A span Rn. Okay. And second part is T is 1 to 1. If and only if columns of A are linearly are linearly independent are linearly independent. Okay, let us see proof of this theorem. First we prove part 1. In part 1, T maps Rn onto Rm if and only if columns of A span Rn. Columns of A span Rm means what? Columns, every vector in Rm is a linear combination of columns of A. Okay? We know that columns of A span Rm if and only if for each B bar in Rm the equation A into x bar is equals to B bar is consistent. In other words, if and only if for every B bar in Rn the equation P of x bar is equals to B bar has at least one solution. This A into x bar is equals to B bar is consistent means T of x bar is equals to B bar has at least one solution, and this is true only if and only if this is true if and only if T maps Rn onto Rm. T maps Rn onto Rm. This is the proof of part 1. Now we will prove part 2. The equation in part 2 we have to prove T is 1 to 1 if and only if columns of A are linearly independent. Okay. The equation T of x bar is equals to 0 bar and A into x bar is equals to 0 bar are the same except for the notation. These both are same. And in previous theorem we have seen that T is 1 to 1 if and only if A into x bar is equals to 0 bar has only trivial solution. Here we say that by known theorem, and that theorem is, or here you can say only by theorem, and that theorem is T is 1 to 1 if and only if A into x bar is equals to 0 bar has only trivial solution. trivial solution. This happens if and only if the columns of A are linearly independent. Okay. This is the proof of part 2. Hence, proof of this theorem is completed. Now we will see next definition: invertible linear transformation. Invertible linear transformation. Definition: a linear transformation T from Rn to Rn is said to be invertible if there exists a function s from Rn to Rn such that s t of x bar is equals to x bar for all x bar in Rn. Okay, here capital X, and t of x bar is equals to also x bar for all x bar in Rn, Okay. A linear transformation T from Rn to Rn is said to be invertible if there exists a function which is also from Rn to Rn such that s of t of x bar is equals to x bar for all x bar in Rn, and t of s of x bar is equals to also x bar for all x bar in Rn. Okay. For example, if A is invertible n by n matrix, invertible means A inverse exists, invertible n by n matrix, then linear transformation T defined by T of x bar is equals to A into x bar is invertible. Okay. When A is invertible n by n matrix, then linear transformation T defined by T of x bar is equals to A into x bar is invertible. Why this is? Because we have S from Rn to Rn given by S of x bar is equals to A inverse into x bar for all x bar in Rn, for all x bar in Rn, and A into A inverse is equals to A inverse into A is equals to In, identity matrix of order n by n, such that S T of x bar is equals to S of T of x bar is A into x bar, which is equals to A inverse, because we have S from Rn to Rn given by S of x bar is equals to A inverse into x bar. So here x bar is A into x bar, so A inverse into A into x bar, which is equals to, obviously A inverse into A is identity, and identity into x bar is again x bar, and also T of S of x bar is equals to what? T into S of x bar is A inverse into x bar, okay, and T of x bar is A into x bar. Here x bar is A inverse into x bar, so here is A into A inverse x bar. Again A into A inverse is identity matrix, and identity matrix into x bar is, you will get x bar, okay, for all x bar in Rn, okay. Hence, if A is invertible n by n matrix, then linear transformation T defined by T of x bar is equals to A into x bar is invertible. Let us write down next theorem. Theorem name is the invertible matrix theorem. Let A be a square matrix of order n by n, okay. Then following statements are equivalent. First is A is invertible. Next, A is row equivalent. To the n by n identity matrix. C, A has n pivot position. D, the equation A into x bar is equals to 0 bar has only the trivial solution. E, the columns of A for linearly independent set. F, the linear transformation transformation x bar to a into x bar is 1 to 1 is 1 to G. The equation a into x bar is equals to b bar has at least one solution for each b bar in Rn. H. The columns of A span Rn. The linear transformation x bar to a into x bar maps Rn onto Rn. J. There is n by n matrix C such that Ca is equals to R. K. There is n by n matrix D such that A into D is equals to identity. And last one is L. A raised to T is an invertible matrix. Okay, we will stop here. Thank you.